Hello everyone, so welcome back. In the previous video we saw about electric flux and now we are going to start with the derivations. So the first derivation of this chapter is going to be for the electric field along the axial line of an electric dipole. In the next video, however, we will see the other part of this derivation, that is in the equatorial plane. So for this video, let's talk about the electric field in the axial line. Okay, let's start with what is an electric dipole first of all. So when you combine two charges, one positive and the other one negative of equal magnitude kept at a distance apart, it's called an electric dipole. That system is called an electric dipole. It constitutes of one positive charge, another negative charge kept at a distance apart. This is an electric dipole. So we assume this distance to be 2L for simplicity in the derivations. So the entire distance is 2L. So there is going to be a point in between which is the exact center for this dipole. So that distance to that center point is taken as L and L. So that the entire distance between them is 2L. So in numericals, when they say the distance between the two charges are like, for example, 2 centimeters, then 2L equals 2 centimeters and not L. Okay, so now let's go ahead and see what would be the electric field in the axial line. An axial line is along the line containing the two charges. This is known as the axial line. And the second derivation would be for equatorial line. And equatorial line is a line passing through the center perpendicular to the dipole. This is the axial line and this is the equatorial line. So we'll find a point in each of these and find the electric field at that point. So first, let's see about the electric field at an axial point in a dipole. So here we are going to let's construct a dipole. We are going to have a positive charge and a negative charge of charge Q. Let's say it's Q, plus Q and minus Q, kept at a distance of 2L apart. So this is going to be L from the center and this is going to be L from the other center. So the entire distance between them is 2L. So now we have to consider a point where we want to find the electric field. So let me take this as the random point. And we have to know what's the distance of that point from the dipole. So whenever we measure the distance of a point from a dipole, it is always with respect to the center of the dipole. So this point is at a distance f x away from the P. So this is the distance we need. So now we can go ahead with the derivation. So the first step is that the electric field at this point P is the sum of the electric fields, the sum of the contributions of these two separate charges. So it's due to electric field of the positive charge and the electric field of the negative charge. So we know the formula for electric field, right? It is just, electric field is the force divided by the charge, F by Q. So electric field is going to be KQ by R square, where R is the distance. So you have to be careful when you take the distance. So what's going to be the electric field due to positive charge at this point P? It's the charge of this point and the charge of this, it's the charge of this point divided by the distance from plus Q and P. So it's going to be K, Q. If you want, you can take the small letter Q since I've used that, divided by, what's the distance between the point P and this positive charge Q? It's x plus L. So it will be x plus L the whole square. Now what's going to be the electric field due to point minus Q? So it's going to be plus K, but the charge this time is negative. So you're going to take with the negative symbol, divided by, what's the distance between minus Q and P? It is this distance and it's going to be x minus L. the entire distance minus this portion is going to give us our required distance. So it's x minus L the whole square. Now we have to simplify this, and it's just algebraic. So let's go ahead and try to simplify it. I'm going to start from here. So you can take k and q constants outside, kq, and you're left with 1 by x plus L the whole square minus 1 by x minus L the whole square. I have just brought out k and q common outside, and I'm just factoring the inside. So now we have to take the LCM of the brackets. So we have kq x minus L the whole square minus x plus L the whole square divided by the product of these both in the denominator. Now let's open the numerator. A minus b the whole square, x minus L the whole square. It's x square minus 2xl plus L square. X square minus 2xl plus L square minus, be careful with minus. So x plus L the whole square, a plus b the whole square is x square plus 2lx plus L square. Divided by the denominator. Now let's do it in the same step. The denominator I'm going to split it into 4 terms. That is x plus L the whole square, I'm going to write it as x plus L into x plus L, and x minus L is x minus L multiplied by x minus L, and you will find out why. Now I'm going to group one of the positives and the other of the negatives, and because a plus b into a minus b, we know how to simplify. It's a squared minus b squared. So that's the purpose of splitting it into 4 terms. So I'm going to rub this and start from the board again. Okay, so now we're going to simplify this. We can remove, first open the brackets on the top. So we'll have x square minus 2xl plus L square minus x square minus 2lx minus L square. This is the numerator. And denominator is going to be x plus L into x minus L, which is x square minus L square, x plus L into x minus L, which is again x square minus L square. Now with the numerator, we can cancel out certain terms, x square and minus x square, L square and minus L square. So we have, this is electric field total. Electric field is kq minus 2lx is minus 4lx divided by these two are the same terms. So it's going to be x square minus L square the whole squared. So if you see, this is actually the formula, this is it. But we can simplify this furthermore with certain assumptions. What we are going to assume is that the distance of the point which we have considered, the point P over here, this distance x is far greater than the distance separating the dipole, that is x greater than L. Because if you see a dipole, in reality it's just very minute, it's very close to each other. So any distance you choose as a point P is always mostly going to be very greater compared to this distance. So what is going to happen is x square minus L square is going to remain as x square. It's because it's like subtracting 50 squared minus 0.002 squared is still going to approximately be equal to 50 squared, because this is a very small term, right? So x square minus L square is going to remain as x square. So when you keep the denominator as x squared, this term becomes x squared, but it's whole squared. So it becomes x raised to 4. Now we can cancel off one of the x from the numerator and the denominator. So we have electric field equals minus 4kql divided by x cube, we can do one more simplification, and that is by introducing a quantity known as dipole moment. And dipole moment helps in understanding how strong an electric dipole is. You have learned this in grade 11 chemistry for ionic charges. So dipole moment represented by P is the distance separating the two charges, which in this case is 2L, multiplied by the charge possessed on any one of the charges, because the magnitude is going to be the same. So its dipole moment is 2Lq. You clearly see that we have LQ and obviously a 2 because of the 4. So let's split it as 2K into 2Lq by x cube. I'm doing nothing here, I'm just splitting the 4 into 2 into 2. So 2K into 2L cube by x cube. And this is what I'm going to replace with P, which is the dipole moment. So we have the final answer as K minus 2P by x cube, where K is the constant we have seen in Coulomb's law. It's 1 by 4 pi epsilon naught minus 2P by x cube. And this negative charge is because of the negative charge is because of the way we have taken the dipole. If we would have taken the dipole with the opposite orientation, and that is by, instead of assuming the dipole to be like this, if we would have taken the dipole to be in this way, then the answer would have been having a positive charge. So the charge, the negative sign does not make a difference here, it just shows the direction of the net electric field. So the net electric field over here, due to the negative charge, as I told you that the point P is a test positive charge. Always when we consider a point for a derivation, it's always a unit positive charge. So I have told that this is a positive charge. So what do you think is going to be the direction of the electric field due to this positive charge? Positive and positive repels. So the direction of electric field at this point due to the positive charge is going to be away from the positive charge, and due to the negative charge is going to be towards. Negative and positive attracts. So you see they are in the opposite directions, but this is going to be stronger. That's why the net electric field is negative. It's in the left hand direction. Over here is the opposite case. The negative charge is going to influence pulling it towards it. But the positive charge, being more closer to the point P, can exert a push much stronger than how much the negative can pull. So the magnitude of the push is going to be greater than the magnitude of the pull. And over here is the opposite way. The magnitude of the pull is going to be greater than the magnitude of the push. And you can find it out by deriving by yourself. We have done it in this case, so try deriving it in this case and you'll find that the negative symbol is not there. So this is the electric field due to a dipole at any point on the axial line. So we have finished the axial point for now. And so now we saw about the electric field in the axial line. In the next video, we'll talk about the equatorial plane. Thank you for watching.